Good morning, students. Discipline is a training of the mind and character of a person to observe self-discipline. The heavenly bodies, ocean currents, winds, plants, and animals move and grow in a disciplined way. Discipline makes life harmonious and successful. It should come from within and should be self-imposed. It means it starts with you. So start working on self-discipline from today. Let's move on to the last part of the lesson, ionic equilibrium. What did we learn in the last class? We learnt about the pH of solutions, buffer action, common ion effect, Ostwald's dilution law, and we also saw Henderson's equation, how to derive the pH of a buffer solutions. In continuation, let's move on with buffer capacity and buffer index. What does buffer capacity mean? We know a buffer solution resists a change in pH. So how strongly it resists, whether immediately the pH changes on addition of an acid or a base, or it takes more amount of the acid to really bring a change in the buffer. That is called as buffer capacity. And once introduce an quantity called as beta or the buffer index. So this beta is measured in terms of gram equivalents of the acid or base that should be added to the buffer to change its pH by 1 unit. So I have a solution here whose pH is 3. Let me say I am adding acid to it. What happens when I add an acid? pH, hydrogen ion concentration increases, pH should decrease by 1 unit, or if I add a base, the pH may increase by 1 unit. So beta is defined as the number of gram equivalents of the acid or a base to be added to bring about a change in the pH by 1 unit. So beta is buffer index, dB is a gram equivalence of acid and base, and dpH is a change in the pH. With this we move on to salt hydrolysis. How is a salt formed? By neutralization of an acid with a base. So this salt, when it is added in water, let us say we are taking sodium hydroxide and hydrochloric acid. What salt will be formed? Yes, sodium chloride. When I dissolve sodium chloride in water, how the ions react with the water and what happens? That is called as salt hydrolysis. We are going to see what happens in the case of 4 different types of salts. The salt of a strong acid and strong base, salt of strong acid and strong base and weak acid, strong acid and weak base, and weak acid and weak base. And we are also going to see the relationship between Ka and Kh and how to calculate the pH of such a salt solution. Let us look at the first case, hydrolysis of a salt of a strong acid and a strong base. Here I have sodium hydroxide and nitric acid. Both of them are strong. So what is the salt form? Sodium nitrate. Now I take the sodium nitrate and dissolve it in water. What do I get? Sodium ion, nitrate ion. Remember, strong solutions are always completely ionized at all concentrations. So now what happens when I add water to this salt solution? Only water will be ionized to give H plus and OH minus. Now this Na, which is the conjugate acid of the strong base sodium hydroxide, will not react with the H plus ion or the OH minus ion. Similarly, nitrate, which is a conjugate base of the strong acid nitric acid, will not react with H plus or OH minus. So in such a solution, what all I have? I have Na plus, I have NO3 minus, and H plus and OH minus. So finally the concentration of the solution depends upon the concentration of H plus and OH coming from water. We know that in water the concentration of H plus and OH is equal, which is 7. That is why solutions of strong acid and strong bases are always neutral. So here I have a salt, sodium chloride. As you can see, when dissolved in water, the sodium ions and chloride ions go separately. They do not react with water, but they are just surrounded by water molecules everywhere. This is chloride ion surrounded by water, sodium ion surrounded by water. So in the solutions, the ions just move away and they are separated and they just stay like that in ionic condition throughout. They do not react with water and form sodium hydroxide or hydrochloric acid. That is why the pH of such solutions is neutral. It is 7. So In this case, because it's completely ionized, it remains neutral. Now let us see the hydrolysis of the salt of strong base and weak acid. Here I have sodium hydroxide and acetic acid. The salt formed is sodium acetate. Now what happens to sodium acetate when I dissolve in water? It forms acetate ions and sodium ions. As we know, sodium ion is a conjugate acid of the strong base sodium hydroxide, so it will not react with water. But whereas acetate ion is a conjugate base of the weak acid acetic acid, and it reacts with water forming acetic acid. So now in this solution, what are the ions I will be having? I will have Na plus, acetic acid, acetate and OH minus ions. The H plus ions is completely neutralized by acetate ions. So here the concentration of the hydroxyl ion is greater than the H plus ions, and therefore the solution is what? It is basic in nature. Now let us try to calculate or derive a relationship between Ka, dissociation constant, and hydrolysis constant Kh. Just like Ka, we can write the hydrolysis constant for this equation as the product of the molar concentration of the product by the product of the molar concentration of the reactant. So as usual, water is in excess, so the equation can be simplified as molar concentration of the products by molar concentration of only acetate ion. Let's do the same for Ka, dissociation constant. So Ka is equal to active mass of CH3COO minus into H plus by active mass of acetic acid. Now let's multiply this with the expression Kh. So on simplifying, what do we get? Ka into Kh. Strike off all this, simplify it, and I get Ka into Kh is equal to product of H plus into OH minus, which is nothing but the ionic product of water. So from this relationship I can write Kh is equal to Kw by Ka or Kb as the case may be. Now let us see how to calculate the pH of this solution. Before that, let us see how to derive Kh in terms of H. From in Ostwald's dilution law we saw Ka, the dissociation constant, is given by what? Alpha square C, and H is given by root of Ka into C. Here similarly, Kh can be derived in terms of hydrolysis constant H or degree of hydrolysis H. So Kh is given by H square C, or OH ion concentration or H plus ion concentration is given by root of Kh into C. Here again I am substituting the value of Kh in the previous slide which we saw, Kw by Ka or Kw by Kb as the case may be. Now let us see how to calculate the pH of this solution using concentration and Ka. We know pH plus pOH is equal to 14, or pH is equal to 14 minus pOH, or what is pOH? Negative logarithm of OH ion concentration. Now what is log OH? Just now we saw OH can be written as what? Root of Kh into C. When I simplify it, I can get Kh into C to the power half. Now let us see what is Kh is equal to Kw by Ka. So we have this expression, and I am going to expand this expression. What do I get? 14 plus half log Kw plus half log C minus half log Ka. This one comes to the numerator, so it becomes minus. Now in this equation, let us substitute these values. We know that log Kw is equal to what? Kw is equal to 10 to the power minus 14, and on simplification I get what? Kw is equal to minus 7, and we know that minus log Ka is nothing but what? pKa. So in this equation, when I substitute these values, we get 7 plus log C plus log half pKa. So any two values are given, we can find out the third value. Now let us see what happens when I dissolve the salt of strong acid and weak base. Here I have ammonium hydroxide as my weak base and hydrochloric acid as my strong acid. What is the salt form? Ammonium chloride. I am going to dissolve ammonium chloride in water. What are the two ions? Ammonium ions and Cl minus ions. So you know Cl minus is what? The conjugate base of the strong acid, hydrochloric acid. It will not react with water, it will not undergo hydrolysis, so it remains as such. But whereas the weak base ammonium hydroxide, which is a conjugate acid of the weak base sodium hydroxide, will immediately combine with water, forming the unionized weak base and gives out H plus. So, in this mixture, H plus ions keeps on increasing. So, concentration of H plus is greater than the hydroxyl ion. That means what will happen to the pH? It will decrease. So, the solution will be acidic in nature. Now, let us see how to calculate the pH of this solution. We know from the Ostwald's dilution law, just like that I can write H plus is equal to a root of KH into. So, we are going to calculate the pH. So, we know pH is equal to minus log H plus. So, already know that KH plus is equal to root of KW by KB into C. Now, let us substitute this value in this equation. So, I get half log KW by KB into C to the power half. On expansion, we get half log KW minus half log C plus half log KB. We already know the value of KW is equal to 10 to the power minus 7 and log KB is equal to PKB. Let us substitute these two values in this equation and we get pH is equal to 7 minus half PKB minus half log CB. So, if I know the value of any two quantities, I can calculate the third one. So, we are going to see the last case, hydrolysis constant of a weak acid, salt of a weak acid and a weak base. I have ammonium acetate derived from ammonium hydroxide and acetic acid. When I dissolve it in water, it gives me acetate ion and ammonium ion. Here, ammonium ion will definitely combine with water, which is the conjugate acid of this weak base ammonium hydroxide and produces H plus. Similarly, acetate ion, which is a conjugate base of weak acid acetic acid, produces OH ions. Now, this H plus and this OH is decided by whether it is from the weak acid or from the strong acid or weak base or strong base. So, here if Ka is greater than Kb, the solution is acidic. If it is less than Kb, then the solution is basic. pH of such solutions is calculated from the expression 7 plus half pKa minus half pKb. Now, we are going to see a next concept called as solubility product. What is solubility product? I take a salt XY like sodium chloride or Al2SO4 thrice or whatever it is, and when I dissolve it in water, I get two ions X and Y. This M and N are called as coefficients, molar coefficients. It means M molecules of X and N molecules of Y is got. Let us apply the mass of action, law of mass action, and derive the constant, equilibrium constant K. As usual, product of the molar concentrations of the product divided by the molar concentration of the reactant. In the case of salt or a solid, the reactant concentration is always taken as a constant. So, then the equation becomes, we won't have the denominator, only the numerator. So, now the constant is denoted as Ksp, which is called as solubility product given by the molar concentration of the constituent ions produced. Now, why do I need the solubility? Okay, let us try to define it. It is called as a product of molar concentration of the ions raised to the power of what? Coefficient in the stoichiometric balanced equation. Why do I need to study about the solubility product? It helps me to understand whether the product or the salt will be precipitated or not when I mix the solutions. You must have done so many volumetric and inorganic salt analysis in the lab, chloride analysis, nitrate analysis, basic radicals and acid radicals. So, when we mix two solutions, we might get a precipitate, we might get a clear solution. Whether we get a precipitate or not is dependent on the solubility product. Let us just see here. I have potassium nitrate solution, which is a clear solution. To this I am adding a solution of potassium iodide. This is lead nitrate, and I am adding potassium iodide. We can see a beautiful yellow color precipitate. Hope you recall golden yellow spangles test. Dissolve the precipitate in hot water and cool it. The precipitate will reappear in the form of golden yellow spangles. So, whether the precipitate will be formed or not is decided by the solubility product. Let us see that. When the product or the solubility product of the molar masses of the ions is greater than the solubility product, then the solution will be supersaturated and precipitation occurs. If the ionic product is less than the solubility product, the solution is unsaturated and no precipitation occurs. And if it is equal, that means it is in equilibrium, the solution is saturated, still it will not occur. Only if it is supersaturated, precipitation will occur. Now let us determine the solubility product from molar solubility. As usual, we have the salt XY. When I dissolve it in water, I get m moles of X and y moles of m. So here it means when I dissolve 1 mole of XY, I get m moles of X to the power n plus and n moles of Y to the power m. Now let us take S to be the molar solubility. Then the concentration is given by X to the power ms, here to the power m to the power n, and this to the power m. Let's substitute them in this equation. Solubility product equation. So I have ms to the power m and ns to the power n. Since S is common, we can simplify and write the equation as solubility product is equal to product of m to the power m and n to the power n into S to the power what? M plus n. So what did we learn in today's class, children? We learnt about buffer index, salt hydrolysis, solubility product, determination of solubility product from molar concentration. Revise the full chapter, all the 3 days which we learnt, and then take up today's Kahoot. Revise all the 3 days lesson, the whole chapter of ionic equilibrium, and then take up the Kahoot, children. Thank you, students. Stay home.